Today, we're joined by Audrey Olivier, a professor in the Civil and Environmental Engineering Department of USC. And she's going to be talking to us about her research on combining probabilistic data analytics and mechanistic modeling for predicting and monitoring structure systems under uncertainty. She got her PhD in civil engineering and engineering mechanics from Columbia and held a postdoc at Johns Hopkins before joining USC. So with that, I'll hand it over to Audrey. And
thank you so much.
You can ask questions during the talk, or I'll raise it on Zoom. If you post on Zoom, I'll raise it in the room. So thanks.
Yeah, feel free to ask questions anytime. Thank you so much for hosting me. My first time great to be here. So as Eric mentioned, I'm civil engineering. So I'm going to start by telling you a little bit how we use data analytics for civil engineering applications. So one of the, actually my background where I started from was in a field called structural health monitoring. And the idea in SHM is that we use sensing data to monitor structures and assess whether they are healthy or damaged. So in this type of algorithms, we combine mechanistic models that represent the mechanics of the structures that we're monitoring and sensing data. And from this, we try to, for example, learn the parameters that govern those mechanistic models to try and detect potential damage. So here, for example, in this example, there is a reduction in stiffness that is actually a damage pattern. So this is one of the way we use data for monitoring civil systems. There is also a lot of work in using data in transportation. So one thing I'm going to be talking a little bit about in this talk is travel time modeling, in particular ambulance travel time modeling. So that's very important when you're trying to optimize emergency medical response to know how much time it takes for an ambulance to travel within the city. And so we've done some work with in New York to use that analytics to help improve EMS operations. And another big part of using sort of predictive analytics and mechanics is through surrogate modeling. So we have a lot of mechanistic models that are very computationally expensive. And we use machine learning algorithms to try and speed up computations. So we build a surrogate model of our complex mechanistic models so that we can run optimization, multi-scale models, things like this. So I'm going to be talking a little bit about this and when it comes to materials modeling and also power grid systems that are potentially high dimensional. Now, one of the issues that comes up often when we look about data analytics for civil engineering is that we have a lot of data deficiencies, if you will. Our data is typically very sparse, and we don't necessarily have, we don't have control over the data collection process sometimes. For example, if we talk about structural health monitoring, we may have a lot of data of the structure in its healthy condition, but when the structure gets more and more damaged, we have less and less data. And yet this is this is what we're interested in. We're interested in learning about damage. So our data set are typically sparse or imbalanced, and they're maybe noisy. So talking about ambulance travel time, there is a lot of traffic, things like this that actually create noise in our data sets. And so something we need to account for. And the problem is that we are trying to use those algorithms for decision making, right? So whether it's in respect with this HM or optimization of EMS, it's kind of high consequence decision making. And so for this to happen, we need trustworthy models. We need to be able to rely on the predictions of our model. And so we need to not just have models that are accurate, but we want to try and assess the confidence in our predictions. And because of this, a lot of the work that I do is in probabilistic machine learning, right? So we try to quantify the uncertainties in our data and our models in order to have confidence estimates around our predictions. So really, my research lies sort of at the intersection of data analytics, mechanistic modeling for civil engineering, but also a big part of uncertainty quantification. So this talk in particular is about Bayesian neural networks, where basically we try to integrate some uncertainty estimation within Bayesian, within neural networks. And so, so I'm going to be talking about how we integrate UQ and how we try and integrate physics within our neural nets through different mechanisms. And I'm going to talk about 3 different applications in material surrogate modeling, travel time prediction, and power grid contingency analysis. So first, I'm gonna sort of set up the framework and the notations that I'm gonna use throughout, right? So I'm trying to learn some kind of a mapping, so a predictive model from an input X to an output Y using some data, and data points here, input output pair. So I'm looking at a regression problem. And the goal is that I want to be able to predict for a new input the corresponding output, right? So in travel time estimation, for example, your input might be the origin and destination locations, the time of day, and you want to predict how much time it's going to take for that car or that ambulance to travel from origin to destination at a certain time of day. And I'm going to be talking about neural networks. And the reason why we use neural networks is because a lot of our data is complex in some ways. So for example, in SHM, we deal a lot with time series data. In materials modeling, we deal a lot with image data of microstructure. So this is a microstructure. And so there's a lot of image data. We also, I'm going to be talking at the end, for power grids, this can be represented as a graph. So we have a lot of graph data. And those neural networks are nice to handle those data through sort of specialized architectures like recurrent, convolutional, or graph convolutional neural networks. So in a typical neural network type setting, in a deterministic setting, you would find the parameter. So throughout my omega is the parameter of my neural network, so kernels and biases, and I'm learning it through some kind of a minimization. So I minimize a loss, which typically contains some kind of a data fit term and a regularization term. And then using this predictor, I can make predictions for new inputs. And typically the way those neural networks are assessed in terms of their accuracy is through computing some kind of an average metric of accuracy, right? So you, in advance, you take a test set that is typically follows sort of the same distribution of your training data because you separate the test set out of your training data. So it's kind of in distribution prediction, and you compute some kind of an average measure of accuracy on that test set. What we want instead is that we want to have granular prediction of how good our model is performing, right? So what we really would like to do is when we make a prediction at a new input X, we would like to be able to predict the mean, but also have some kind of a confidence bound around that prediction that tells us, the neural network is telling us, okay, around here, I know what I'm doing because I've seen quite a bit of data there. But in regions of space away from data, then it doesn't necessarily know exactly. It's not necessarily that confident. And the important thing about this is that this allows us to sort of have an assessment of accuracy both in and out of distribution, right? And so typically when we work with models that are deployed, we have out of distribution predictions. And so this is important to have this type of accuracy assessment. So now so basically what I'm trying to do is embed uncertainty quantification within neural networks. So now where do the uncertainties exactly come from in our examples? We typically separate into two different types of uncertainties, what we call aleatory and epistemic. The aleatory uncertainties are everything that relates to data noise, sort of like the inherent stochasticity of the data generation process, or everything that we are not modeling. So for example, if you're modeling travel time and your input is origin, destination, time of day, maybe weather actually also have an impact on travel time. But if you're not modeling it, it actually becomes noise. So everything that you not model, there is also, so with respect to sensing, so our sensors are not necessarily perfect, and so we may have noise in this scenario. So that's the aleatory uncertainty, and then the epistemic uncertainty in the sort of machine learning realm, it comes from lack of data. Right? So this is where those places where I'm trying to train my model, but I don't have a lot of data. This is where I'm going to have epistemic uncertainties. And I'm trying to quantify both of these uncertainties. And because they come from two different, they have different meanings, we actually quantify them in different ways.
Just a question.
Of course.
So you're taking the aleatoric uncertainty to refer to in distribution data, whereas epistemic is purely for out of distribution. Is that right?
Yes. So you would have also aleatoric uncertainty sort of out of distribution, but typically the way you learn it is where you have data.
Right. Okay. But epistemic is purely for out of distribution. That's how you're defining.
Yeah.
Okay.
So the way that we model aleatory uncertainties is through a likelihood. So the likelihood is so probability distribution, which basically tells us that given an input X and a model, so a neural network with a certain set of parameters, my output is still going to be noisy. So even if I know the input and I know the model, I still have noise. So that's why I have a probability distribution over Y. And the basic assumption is homoscedastic Gaussian, which basically means that you assume that this probability distribution is Gaussian with a constant variance. So something like this. So basically your neural network is predicting the mean of that Gaussian, and then you assume you have some kind of a constant variance. You may know or not what it is. You can learn it from data, but it is constant. And if you then maximize the likelihood, so basically the likelihood is just this, but over all the training data, then this is actually equivalent to minimizing the mean squared error. So this kind of goes back to basic sort of mean squared error regression training of typical neural networks. Now, so I'll talk about this a little bit later, but in most of our data sets, this assumption of homoscedasticity and even Gaussianity is actually incorrect. So in many, so whether it is with this actual like ambulance travel time data or surrogate materials modeling, we have an uncertainty that is just not, the variance is not constant. So there is some kind of heteroscedasticity in here. And so we actually typically use more different versions of the likelihood. So I'll get back to that later. And then when it comes to the epistemic uncertainties, the way, at least in Bayesian neural networks, we quantify this is by learning a probability distribution over the parameters rather than just learning a single value. So in deterministic training, you learn a single value of your kernels and biases by minimizing some kind of a loss. In Bayesian neural networks, you're instead trying to learn a probability distribution. So this is what I'm trying to represent here by those little distribution here. So everywhere you have weights, kernels, and biases, you actually try to learn a distribution over the neural network weights. And this distribution over the weights propagates to then have a distribution over your output. And mathematically, the way we do this is by applying Bayes' theorem. So this is Bayes' theorem. This is my life, sort of. The idea behind Bayes' theorem is that when you're trying to learn, so this is the posterior density, so this is the conditional density of your weights given your data. So this is what you want to learn. And this depends on two different terms. So the likelihood, which we've seen before, that likelihood depends on your assumptions about the aleatory uncertainties. And this is kind of like the data part. And then it also depends on the prior. So the prior is a density over the neural network weights, which is supposed to be giving you an idea of what you think your parameters should be prior to having seen any data. And we're going to see that this is not necessarily that easy to set for neural networks, but so I'll talk a little bit more about that later. If you only learn, so in Bayesian inference, we try to learn a full distribution over this parameter vector. If you're only trying to learn the maximum, so the mode of that distribution, so that where this distribution is maximum, and you make so the almost mechanistic Gaussian likelihood and assume a zero mean Gaussian prior, so for this part, then what ends up happening is that when you're trying to maximize this posterior distribution, you actually end up with the exact same loss as mean squared error loss with an L2 regularization. So basically what that means is that the likelihood is your data fit term, and the prior is your regularization term. So if you set a zero mean prior, it basically means that you're telling your algorithm, I think my neural network weights should be close to zero to start with. And this is the same as regularizing, where regularizing, you're trying to bring your neural network weights to be close to zero to avoid having a model size too complex and that overfits. So this was all in sort of the parameter space, right? So we're trying to learn this posterior density in the parameter space. What we're really interested in at the end of the day is how does this distribution in the parameters, the neural network weights and kernels and biases, how does that propagate to the output? Because what we want to do is have an uncertainty prediction on the output, not really the weights themselves. And so both the likelihood and the posterior sort of propagate to your output. And at the end of the day, if you compute the variance of your output, so the conditional variance of your output for a new input given your data, you can decompose it into, again, those two terms, an aleatory term and an epistemic term, where the epistemic uncertainty comes from the variance over your neural network weights that comes from that probability distribution. And the aleatory term is more related to the variance over your likelihood term. So now, why is this challenging? The reason why this is really challenging is because applying Bayesian inference in a high-dimensional space is really hard. So learning a probability distribution over the space of the neural network kernels and biases, which are typically really high dimensional, is really hard. And then because neural network weights are so high dimensional, but also non-physical, right? So they are not parameters that hold some kind of physical meaning. It's really hard to define a prior over them. So typically when we work with mechanistic models, the parameters that we have, they have some kind of a physical meaning, right? They can be a stiffness. So because they have physical meaning, it's easier to set a prior from physics intuitions. But in neural networks, it's not easy to build a prior in the parameter space. So basically two things are hard: setting the prior and then going from the prior and likelihood all the way to the posterior, so performing Bayesian inference. So there's been a lot of research on developing methods to do Bayesian inference in neural networks. So this is probably where most of the work has happened. And so there are several ways that you can basically estimate this probability distribution. So it's not, this problem is not tractable, so you cannot compute it analytically. But you can find approximations of this posterior density. You can do it through sampling. So this is probably the most accurate way of doing it, but it's extremely computationally expensive, right? So you learn, you sample and you end up with samples that are representative of your posterior distribution. You can do it through variational inference, which basically instead of sampling, you assume that the density you're looking for is follows a certain known distribution. So for example, if you assume it's Gaussian, then you know that the only thing you need to learn are its mean and its standard deviation. So you sort of simplify a problem of learning a really complex distribution to learning something that's a little bit simpler. And so you can transform that into an optimization problem, which is it's better with, so neural networks, there's a lot of work on optimization, so it's useful to do that. So we've done some work in this realm because the accuracy of this really depends on the complexity of the distribution that you assume. And so we've looked at things like multimodal variational inference, things like this. Another line of sort of inference methods that actually work really well in practice are ensembling schemes. So in machine learning, there's a lot of work on ensembling, right? So you, instead of just learning one models, you train a bunch of them and then you take an average over all the predictions, and that helps typically perform better. But it also allows you to predict uncertainties, because where your models disagree is where you have typically sort of high epistemic uncertainty. So deep ensembles were first introduced in 2017. They are not Bayesian per se because they do not have this notion of prior. And the notion of prior is very important. Bayesian inference is one of the core principles. And so deep ensembles per se are not Bayesian, but you can sort of modify the algorithms, and there are things like ensembling with anchoring or ensembling with randomized priors that basically modify a little bit the ensembling schemes to allow consideration of the prior. So just to give an overview of what that is, because this is what I'm going to be using in a minute. In ensembling, you train now set an ensemble of neural networks, but you train them all deterministically. And you train them by minimizing some kind of a loss that is slightly different than, so all the neural networks in your ensemble are trained on a slightly different loss. And in particular, the data set that you use to train all these neural networks is slightly different. It's bootstrapped sampled. So basically, every neural network sees a slightly different data set. And then in ensembling with anchoring, you also regularize each of these neural networks to a sample from your prior. So this is how we integrate this notion of prior within Bayesian, within this anchoring scheme. So you sample so a set of weights from your prior, and then instead of regularizing to 0, which is typical regularization technique, you regularize to this prior sample. So basically what that means is that each of the neural networks in your ensemble, they are trained to fit a slightly different data set. And you are trying to regularize them to a slightly different starting point. And so this helps preserve diversity in your ensemble. So all your neural networks are different, but yet they are still trained on your data. And then by taking statistics over your different neural networks, you get an estimate of your mean prediction and the variance, which is, so here is just the epistemic uncertainty. Basically, it's the variance of the neural networks. Yeah.
The priors here, the sort of zero mean Gaussians that you were talking about before, or there's something learned from the data more directly? That's
a good question. So, so it can be whatever you want it to be. So in if you don't know, then you probably assume that this zero mean prior. But I'm going to actually talk in a minute about a way to integrate more information into your prior.
Thanks.
And so to that question, so as I said before, there has been a lot of work in Bayesian neural networks on how to design inference algorithms, right? So HMC, variational inference, ensembling, things like this. But in our group, what the thing that we really work on is the prior. And the reason for that is because the prior really matters in Bayesian inference. So here what I'm showing is for a certain prior for my, so this is a zero mean with a certain variance. And then I'm running HMC and I'm running anchored ensembling. And I get a posterior, so I start with a really small prior, and so I have a really small posterior uncertainty. And then if I increase the variance of my prior, then I end up having a lot more posterior uncertainty. But basically what I'm showing here is that the prior somehow matters more than the method that we use for inference. So there has been a lot of work on inference methods, but there hasn't really been a lot of work on how do we set the prior for neural networks, and it matters a lot. And the other good thing about the prior is that since we come from, I work a lot with mechanistic models, in theory, it's a way that we can integrate information, right? A priori information about the models that we have. So now this prior information that we typically have, so let me see there, okay. So this prior information that we have is typically available to us in the function space rather than the parameter space, right? Whereas before, the kernels and biases, they are totally non-physical. So we don't really know what they should be, but we may have some prior information about the mapping from X to Y. That can be from different data sets. That can be from low-fidelity simulations that are easier to run. We can run many of them. So we typically have sort of function space knowledge, and the question is, how do we translate this information from the function space back to the parameter space in our neural network, right? So there is a mapping, but it's not a one-to-one mapping because this is really high-dimensional, and so it's not a one-to-one mapping, so that's what makes it kind of complicated. But there is a mapping between the prior, the density in the parameter space and the density, the predictive density in the function space. So the question is how we know how to go from here to here, but how do we go from here to here? It's a bit more complicated. So what we've been looking at is we try to kind of play with different types of priors, and we try to see, okay, how does that affect, so different functional priors, how does that affect our neural network weights? So here, what we did to do this, so this is a 1D problem, right? So we go from an X to Y, but we have different types of prior in the function space in the sense that these are pretty, this is a very constrained prior, right? In the sense that if you know a point, because it doesn't allow a lot of fluctuations in the space, if you know a point somewhere, then you kind of know your curve throughout. Whereas here, you have much more flexible function space priors. Then we also played with some other things. And so we were trying to understand how does this function space prior affect the neural network weights? And so what we did is that we sampled from those priors, and then we trained neural networks. Yeah, we trained neural networks to those functions, right? So I trained an ensemble of neural networks to all these functions, and I look at the resulting distribution of my neural network weights to kind of get an insight about what's happening. So what we saw, so here just sort of snapshots of the distribution in one specific hidden layer. And so we saw some non-Gaussianity in the neural network weights. And something that we were expecting is that when you increase the prior flexibility, you increase the prior variance. Basically, if you remember, setting a prior and regularizing are sort of a one-to-one thing, right? So if you have a very wide prior, a larger variance, it basically means you're not you don't have a strong regularization. You're letting your neural network do whatever it wants to do. And so that's a very flexible prior. So we end up with high variance for very flexible prior. So that's sounds about right. The other thing that we saw is that there was correlation between the neural network weights. And so that is key because in most applications of Bayesian neural networks, people assume some kind of maybe a Gaussian prior, but they always assume that the weights are not correlated because it makes it a lot easier, because when you have a really high dimensional space, learning correlations in this high dimensional space is really high, right? And so typically people assume uncorrelated weights, but we did see that there's different correlation patterns in our in the resulting neural network weights. Now, how we actually estimate this correlation is because we have an ensemble of neural networks in dimension, let's say maybe 50 or 100, we actually do not have a full rank covariance. We have a low rank covariance that's learned using we can actually learn it using an SVD decomposition of our data. And so because of this, we can represent this correlation matrix between the neural network weights just based on the output of our singular value decomposition. And the part that's important is that we're going to be able to invert, because at some point we're going to need to invert this matrix. But now this becomes possible because in order to invert this, you only need to invert the S matrix here from the SVD decomposition, and this is diagonal. So this is very easy to invert. So you have a low rank approximation of the covariance that's basically is amenable to computations. So now how do we leverage this? So if you recall, I was talking before about ensembling with anchoring. And basically this is what we do. So we assume that we have some data and a functional prior. That's our starting point. So the functional prior is basically, we have a way to sample functions in the function space that are representative of our prior. And I'll talk about how we do that. But so basically we have a prior in the function space and we have data that we want to train on. So first we pre-train our ensemble of neural networks to our sample, our functional samples from the functional prior. So that gives us a set of pre-trained weights. Then from those pre-trained weights, we do our little SVD decomposition, we get our low rank matrix. And then we train all these networks to the data. Same thing as before, we actually use the resample data for each of the neural networks. So each of the neural networks see a slightly different version of the data. But now the part that's important is that when we do the anchoring, so the prior, we actually use a multi-dimensional Gaussian, and we consider correlation between our neural networks weights, because we saw that this part is actually key to encoding prior information in the function space. And this I need to invert, but we can invert through our SVD decomposition. And then we take statistics to get estimates. So this is a 1D example of how this works. I start with 2 different priors, where basically I assume that I know my function is somehow increasing from left to right. And so those are 2 different priors. This is a much more flexible prior than this one. And basically when we perform the algorithm that I told you before, the posterior predictive density that we get is something like this. So in the case of a highly flexible prior, I have much larger predicted uncertainties because the algorithm is sort of able to, between here and here in interpolation, the algorithm is actually able to predict some pretty complex functions. But if I start with a functional prior that is very constrained, then it's actually predicting much smaller uncertainties, because it knows, if it knows that point and it knows that point, it actually doesn't have so many ways to go from here to there. And so predicting uncertainty in interpolation with neural networks is really not easy. Like the extrapolation part is kind of okay, but the interpolation is typically where most algorithms tend to underestimate uncertainties. So this is where this considering the correlation between the network weights is really important. So to go to an actual example, so this is a surrogate materials modeling example where I have a two-phase microstructure. So my inputs are some geometrical and material properties of my material. And then I want to understand how this composite material performs as a whole, right? So I know the material properties of both materials, the blue and the orange, but I want to understand how it works as a whole. And so my outputs are basically Young's modulus and things like this of my whole microstructure. And typically the way this is done is by running finite element simulation, which takes quite a bit of time. So we want to build a surrogate that goes from our material inputs to our homogenized outputs. So I have 4 inputs, 5 outputs here. It's a kind of small problem. And so we do this scheme, and we assume a prior mean that is actually a pretty simple function of volume fraction. So we know volume fraction affects quite a bit the outputs. So we just assume a very simple model that prior mean that depends on the volume fraction. And then we use some kind of a Gaussian process to sample function around that mean. And the other good thing about this is that we can actually ensure positivity. So we know that all our outputs have to be positive because they're physical quantities. So those kind of things, like if you want to ensure positivity or if you want to ensure that they belong within certain bounds, you can do that in the function space. So you sample from this function space, you ensure that you apply your right constraints, and then you apply the algorithm by training your pre-training your neural networks and training it to the data. And so the way we kind of check that this works is that we always sort of try increasing the amount of training data little by little and see how that works. And so here, what we can observe is that as you increase the amount of training data, you have better prediction, right? You're closer to the true. So this shows the low. So basically this, right? So this is one of the things that I'm trying to predict, which is basically the plasticity low of my microstructure. So I do that for the 4 rows are 4 different test points for my test set. And so as you increase the amount of data, when you go down, your predictor becomes better. So I have less error, but I also have smaller epistemic uncertainties, right? And the important part is that even when I do not have a lot of data, sure, I'm not correct in my predictions, but I do predict a large amount of uncertainty. So my algorithm is telling me here, I'm not sure what I'm doing. So I'm predicting large amounts of uncertainties, and that's correlated with large amounts of error. So that's the correct way to go. And so those are sort of the metrics. So when we start predicting uncertainties in neural networks, you need to check a bunch of things. You need to check accuracy of the mean, but you also need to check whether your uncertainty is well calibrated. And so we typically use different metrics to check different things. So the root mean squared error is typically telling you how is your mean, so your mean prediction of performing. And so as we increase the amount of data going from here to here, we have sort of a better estimation of the mean. But then our calibration, so the calibration is basically tells us how well our estimated uncertainties are those estimated uncertainties correlated with the error, right? I want a model that predicts high uncertainty if it makes large errors and small uncertainties when it's made small errors. So this is the notion of calibration. And so we check that our calibration is correct. And one thing that is interesting is we also have an out of distribution test set. So in distribution is just we generate the data in the exact same way for the training and the test set. But we also create another test set where we basically sample the data in a different way than what was used for training. So it's an out of distribution type data set. And what's interesting here is that the mean, so if we compare for 50 data points, so the in distribution and out of distribution data are, our algorithm is not performing as well in terms of the mean, but it is still very well calibrated, meaning that actually predicts larger uncertainties here in out of distribution data. So again, this is sort of what we want. We want it to predict high uncertainties when it's not sure what it's doing.
Could I just ask a question? How you measure the miscalibration? I mean, you're looking at the predicted confidence interval and asking like what fraction of the training points?
Yeah, that's confidence interval. Yeah. So basically we plot these curves. So those are calibration curves. And so the miscalibration here is the area between, so a model that's perfectly calibrated is a model for which those curves would be exactly on the line, the XY line. And basically what we plot, so we looked at the scaled residuals. So the error divided by the predicted uncertainty. And we would expect those scaled residuals to follow a standard Gaussian.
And that's the error over what? I mean, that's over a test. There's over a test set.
Yes, it's in a test set. So a test set for each point in my test set, I compute the error, I divide by the predicted uncertainty at that specific point. This should follow a standard normal. So here what I'm plotting is the quantiles of a standard normal, the ECDF of a standard normal versus the ECDF of my normal residuals. And so the miscalibration area is how far is this curve from the x equals y line.
Thanks.
Thank you. So all of these results, by the way, are in a paper that was published in Computer Methods and Applied Mechanics and Engineering a few months ago. And so I just want to finish 5 minutes on like two topics that sort of relevant to on how we also try and include physics information within our algorithms. And one way is through sort of likelihood design. So this is this problem of travel time prediction, where I have some kind of so origin, destination, departure time, and I'm trying to predict the travel time from my origin to my destination. So we have a lot of aleatory uncertainties because there is traffic, so that there's sort of a very stochastic process. And then we have epistemic uncertainties because typically we have a lot of data for short trips, but because your ambulances, typically you send the closest ambulance, so you have more data for short trips than for longer trips. So it's a very sort of imbalanced data set. And then we have also access to a road network, which, so basically it's sort of, imagine this is Manhattan. So we know where the roads are, and so you can build a road network that helps you predict, it gives you an idea of the travel time. But typically those road networks are trained on using sort of car data. Like think about using Google Maps, right? But ambulances travel differently in a city than cars. And so, so this is not perfect, but this is kind of a good starting point. And so one of the main things that we saw there is that the assumption of the homoscedastic Gaussian noise is very, very wrong. And this agrees with the literature on imbalanced travel time, where basically what's happening is for very short trips, you have sort of a lot of uncertainty. And then for longer trips, maybe you start you on an avenue or a highway, and so then traffic matters less, and so you actually have this if you're looking at the uncertainty, it starts really high and then it kind of converges to some kind of a flat line. So basically, the amount of uncertainty, the amount of noise in our data, this depends on the distance traveled. It's not constant over the full data set. So the way we integrated this is it's actually a log normal likelihood, because everything is positive. So we use log normal instead of Gaussian. And then we have a coefficient of variation that is actually input dependent. So that's what we call heteroscedastic. And then we have our prior, which I just talked about, which is our road network, which allows us to have some kind of a prior ID and a prior uncertainty on what those travel times should be. And at the end of the day, you can do the exact same thing as we did before, except that now because you have a different likelihood, this is going to change the data fit term, right? So before, my data fit term was a mean squared error because I had a Gaussian likelihood. But now all of a sudden I have something that's non-Gaussian, which is perfectly fine. You can just do the math. You end up with a different data fit term, but you can use the exact same algorithm. And then if you have a prior, so first it was our road network, you can have some kind of a regularization without the correlation between the weights. And once again, what we saw is that if you add information from the prior, you have a better prediction in the mean, because it's basically helping your algorithm generalize better. And if you have a good likelihood design, then you have we measure that using the log predictive density. So once again, basically, this is just to say that when you start optimizing, when you have both mean and uncertainty prediction, you need to look at different metrics of accuracy. So it's not just the root mean squared error, but you need calibration and things like this. And this algorithm, what it ends up doing is that it really reduces uncertainty only where you have data. So here we have data for short trips. It reduces uncertainty where you have a lot of data, but when you don't have data for longer trips, it remains as the same prior uncertainty. And really quick, so last example is last example on how we use data analytics and neural networks for a simulation, sort of a power grid problem, where so if you might imagine a power grid, right? So you have some loads, so places that consume energy, and you have generators, places that generate energy, and then you have a grid that connects all of that. And the question is, what happens if part of that grid fails? So either a generator fails, a line fails because of weather, because of whatever. And if you have a large grid, it's actually really hard to assess because there are many, many ways that this grid can fail, right? If you have many, many lines, you have a lot of, because every time you need to run the simulation to understand how the power flows within the grid. And if you have a lot of potential contingencies, you need to do that many, many times. So this is where we use neural networks to surrogate the power flow solver. So this is work in collaboration with the Idaho National Lab. And once again, we want uncertainty quantification because you want to be able to make decisions based on your prediction. And here, one thing that is good about this, so this is a high input output problem, right? Because I'm trying to find some power related quantities at all of my generators and loads. And so for a large grid, this is a really high input, high output problem. But we know the grid, right? And even if there is a one contingency, then that line disappears, but we still can represent that as a graph. And so the way we do this is that we integrate that within graph neural networks. So in particular, we use, this is a graph convolutional neural network. So basically, the idea is that we create this adjacency matrix, which tells the algorithm what inputs and also outputs are connected to each other. And so, it just works a little bit differently than sort of fully connected neural net. And then the other thing we have access to, once again, this is very typical in the problems that we look at, we have low fidelity models. So in the power flow is not, solving power flow is a nonlinear problem, but you can run a linear approximation of it. And so this is actually helpful. And so this in some way is also sort of a prior. So here in this specific example, we use it as sort of a residual training. So we first run the low fidelity model, and then we try to learn the difference between the high fidelity and low fidelity model using our neural network. So this is another way that you can integrate prior. And sort of same results as before. The prior is in the snapshot. The prior is in gray, and then the posterior density, the posterior predictions for different types of contingencies are in colors. And basically, this is the blue is where I have most data, and the orange are what we call n-2 contingencies. So I take multiple lines at 2 lines away at once, and so I have less data for this type of cases, and so I have larger posterior uncertainties. So basically, the algorithm is telling me it's not that predictable. So in conclusion, so in the type of work that we do, we really try to, we use predictive models, but we want to be able to use them within decision making at the end of the day. And so this requires uncertainty quantification for trustworthy machine learning. And this is not just about accuracy. We need to assess how good our uncertainty estimates are. In theory, the Bayesian framework is really nice because it allows you to quantify. It has a really nice way of quantifying aleatory and epistemic uncertainties. And you can also integrate prior from prior information. So in theory, it's very nice. In practice, it's hard. But so try to present some solutions to do reliable Bayesian neural networks. So one big problem with Bayesian neural networks is that they're very prone to underestimate uncertainties. And so this is need to be careful how you assess uncertainty. And so I want to thank my collaborators and funding from Audrey in particular, Google for the embeds, and my students, Nihan, Javad, Nicolas, and Osgay, who are doing the work. So thank you very much. And if you have any question, I'm happy to answer them.
Yeah, if there are any questions in the chat, you can raise them or you can unmute yourself. I had a question about the idea of like correlated priors, I guess. It comes from the bootstrapping mostly. Is that the intuition, or is it also maybe coming from using the same architecture for all the models, if that makes sense? Yeah, so one thing that I didn't mention, but that is actually really important when we look at correlation between weights, is that, so I train, let's say 15 neural networks, I pre-train them, so all of them, they are fitted to a different, basically a different function. And so, yes, so one thing I didn't mention, all the neural networks have the same architecture. And also, I do not start them randomly. And this is actually really important because, so typically when you initialize a neural network, you sample the weights at random. And the problem is that if you do that, and you have, so 50 neural networks and you sample the weights at random, then you start from different points.
And so when you pre-train them to different functions, you actually end up with zero correlation. But that comes from the fact that they were randomly initialized. So instead, what we do is that we initialize one neural network randomly, and then we pre-train all of them starting from that specific point. And so what that means is that really the correlation captures how these neural networks have diverged to go through different functions. So the problem is that, so neural networks, because you can sort of swap neurons and end with the exact same function at the end of the day, capturing correlation, you need to be careful how you actually do that.
Okay, interesting. Thanks.
I guess, I mean, so this is sort of like the neural network identifiability issue. And if you had more complex structures, would that be even harder? Because would you potentially see at higher order so if you want expressivity, you would want higher order representations, but then you get potentially into this identifiability issue where the different networks based on slight input changes in the prior would create different latent structures for to represent the signals. So have you seen that, or is that something, because you're constraining the structure of the models, you don't see as much?
Yeah, so this is a really good question. So we for now we've done this with simple fully connected. So it's in the fully connected layers. But for example, if you start to have convolutions, things like this, then I don't know how that's actually going to affect the correlations. I don't know if we need to capture the correlations within also the convolutions and the dense layer that typically happen at the end. So I think this is so because we use the SVD, you can go to sort of larger scale neural networks, but I wouldn't say that you can go to like really, really complex type of architectures. But also it's something I'm never going to do, because the type of problems that I have, I never had that much data. So I'm never going to go and look at, I don't know, a transformer or something where you have, and I need some kind of inductive bias, because I typically deal with small amounts of data. And so I can sort of do this kind of things. If you start really looking at really complex architecture with no inductive bias, but that require really large amount of data, I wouldn't say that this can necessarily move to. And I think the correlations would be so.
Well, at the end, you were talking about these like graph structured problems, and there you would see discontinuities where you might need more expressivity than a fully connected single layer, right? And so, I mean, I think that's kind of like a cool frontier that you're at. I'd be interested to hear more about.
Yeah. So this is sort of what we want to do next, is like those convolution and graph convolution, and seeing how does the correlations work in those spaces, which we haven't done yet, but we want to back. Yeah.
Well, last call for any questions in the chat. Anything?
You had a nice example showing as you increase the amount of training data for your different choices of priors. Yeah, that one. Now, this example here is purely a single fidelity model, right? There's no low fidelity training data that you're using. This one.
So here I do have a prior that is, so this mean function that depends on volume fraction. Right. And so yeah, so I don't have low fidelity data. I have sort of a really low fidelity model, if you will.
I see. Okay. All right.
But you could also start from zero.
Right.
From a zero mean kind of.
Because I think you also had an example where you were using low fidelity data as well, right? You had a sort of a multi-fidelity example. And I guess what I was wondering is whether, presumably, you would see the same effect with your choices of priors as you change the ratio of high fidelity to low fidelity training data. I mean, you should see your uncertainties improve, of course, if you have a higher mix of high fidelity data.
Yeah, that's a good question. We haven't.
Interesting.
So yeah, the ratio of the two.
Right. That's something that should again kind of hold across your different choices of priors.
Yeah.
So I think that's would be an interesting thing to.
Yeah, that's a good point. We haven't looked at that.
Okay, since no one in the chat is like, posted anything, we can end here. But thanks, Audrey, again for
thank you so
presenting.
much.